This is Chapter 2, Investigating Geologic Questions, Lecture 2. We talked a lot about the geologic timescale at the end of the last lecture. Now let's move to data versus interpretations. So we'll start with observations. At this particular rock, with a geologic hammer for scale, some observations could include the characteristics of these deposits of pumice and volcanic ash, including the size and the shape of the fragments and the thickness of the layers. The rocks are light gray, they've got layers. Some layers are thicker than others. They have small and rounded fragments and lightweight fragments with holes. You could make an interpretation there and say, based on deposits that we find from modern volcanic eruptions, this rock is likely pumice, with layers that reflect changes in the intensity of the eruption, and the finer material represents times when the eruption was less active and explosive. So, your interpretation is tied to the type of eruption, the representation of the layers, and the actual type of volcano. Okay. We can think as well, again, about observations versus interpretations. You can make observations here, like I see some vertical fractures and then blocks of rock, bedded rock layers that are falling down. You could ask a question about each observation, like why are these things separate from the rest of the rock unit? And you could propose one or more explanations or interpretations for some questions. So here it's like, I observe that these blocks are separate. Why are they separate? It appears that perhaps these fractures are unloading fractures, that with weathering at the Earth's surface, the rock separated from the rest of the unit and is now going to tumble down the mountain over time with increased weathering and erosion. Now, there are different steps in a geologic investigation. The first step is to make an observation or multiple observations, recognize a problem, and state the problem. So at the top here, we have an observation. We find that there's gasoline in groundwater. We can ask some questions based on that observation. There's kind of a tank here, there's an aquifer here, and there's a well where we're getting gasoline in the water. It's bad. Is that gasoline from a leak in this underground storage tank? We can propose several explanations or hypotheses to answer the questions. Well, it could be from the tank. If it's from the tank, we'll see the same type of gasoline that's in the tank in groundwater. If it is not from the tank, perhaps it's a different type of gasoline, different chemically, and it's coming from somewhere else, and we're intercepting it at this well. If the tank is the cause, the leak should be found in the tank. You can collect data to test your prediction. If there's no leak in the tank, or if the gasoline in the tank is different from what you find in groundwater, it's probably not the tank. You can conclude then that contamination came from elsewhere. That is like an environmental investigation that uses knowledge of geology to figure out what's going on. Okay, there's a few different types of reasoning we can discuss. One is inductive reasoning. With that, you can use a series of examples to construct a general rule. For example, you can observe that there are many debris flows that come about after wildfire. The general rule might be that wildfires set the stage for debris flows because there's a removal of vegetation and a huge amount of erosion with the presence of water that results in these debris flows. So you have a wildfire, you can induce that you are at risk for debris flows. Deductive reasoning can use a general rule and apply it to explain a situation. So we have gravity. The well understood force of gravity caused blocks to fall, slide, and roll downhill on this hillside. It's due to gravity. We're deducing that. Let's talk about this crater. We'll observe this scene and think of options for all the ways that this crater might have formed. This is Meteor Crater in northern Arizona. Meteor Crater. So, if we were to go to the rim of this crater, we can observe these rocks. We've got blocks that are mostly shattered limestone and sandstone. Those are the same types of rocks that we find beneath this region. These blocks are interpreted to somehow have been thrown out of the crater. They're angular now. Okay. The same crater has a geologic cross-section. It's found within sedimentary layers like such. Looks like something happened here to change these formerly horizontal layers. The layers are flat away from the crater, but they're disrupted by the crater. They've been bent, shattered, tilted. Rocks below the floor of the crater are hidden by a thin cover of loose rocks and sand. We can't really see that in this diagram. We can use various models to explain the formation of the crater. Like perhaps there was a volcanic explosion with the source of magma coming from underneath. It blasted open the crater. It threw ash and rock fragments outwards. Perhaps there was a rising mass of salt that's less dense than the surrounding rock. It pushed up the rocks, and then salt dissolved when it was exposed to weathering. Or perhaps impact of a meteor formed this crater and messed up the rocks that were existing there. What type of data would we need for each? And you'll actually use that in your exercise lab 1. I guess for each of these scenarios, I want to know, like, what's the evidence for magma being here? Do we have the rocks that reflect volcanic activity or not? If there's salt, do we have any evidence for salt compositionally? And with this meteor impact, do we have shattered things, shattered pieces of rock that are reflective of an impact? So there's a few different pieces of data we'd like to have in order to figure out how that crater formed. And honestly, it's called Meteor Crater, so we're kind of looking at this scenario right here. But we don't just know that immediately. There needs to be observations and interpretations. And then someone called it Meteor Crater. And we'll stop there for today.